So welcome. This is the special session on the topic of revising natural disturbance emulation in the 21st century Boreal forest. This special session has been proposed and organized by Stephen Mayer, but this morning he woke up without his voice, so I'm taking over, Marie-Josée Fortin. And because of this, the first talk that he was supposed to give is not going to happen. So we reorganized the schedule, and a few other person also were sick. So basically, this is the new schedule, and each speaker will have 12 minutes for their talk and 3 minutes for questions. But we have a lot of time for open question at the end, and we will. We'll tackle those kind of questions as a source of discussion.
Well, thanks everyone for tuning in today to this session. The name of my talk is Implementation of Ecological Forestry, a case study from the Boreal temperate forests of Eastern Canada. And so I think it's safe to say over the last 20 or 30 years that jurisdictions across North America have been making a transition from more traditional sustained yield forestry to this so-called ecological forestry, with ecological forestry being a model of forestry that emphasizes the maintenance of natural ecological conditions through which the sustainable provision of goods and services to meet the needs of society is achieved. And you know, based on that definition, the biggest thing between the two models of forestry really would be an ecological forestry that the focus is on not so much on wood supply anymore, but on the maintenance of ecological integrity. And this is certainly the case in the province of Nova Scotia on Canada's east coast. Nova Scotia is my home province, a pretty little province there, and the forest there would be considered primarily a Acadian forest, which is a transition between boreal and temperate forest. Some people call it hemi-boreal. And it's a unique situation there, and one of the things that makes it unique is the long history of influence of people. The indigenous peoples have been there for 5,000 to 10,000 years, and then but in terms of European North American standards, Europeans have been there a long time. In fact, it's one of the first places in North America where there was permanent European settlements. In 1605 was when one of the first settlements was established there. So more than 400 years of post-European colonial settlement. And so that's had, of course, quite an effect on the forest of Nova Scotia in terms of timber harvesting and land clearing, invasion by non-Indigenous species. And this has changed the character of the forest. And so to that effect, a couple of years ago, the government there held a public plebiscite called the Independent Review of Forestry Practices. And it was a survey of the citizens of Nova Scotia and forestry sector in terms of how they feel about the forestry situation there and how the forest of Nova Scotia should be managed. And through that plebiscite, one message that came through, a strong recommendation, was that the forest of the province should be managed using a philosophy of forestry akin to this ecological forestry. So at the core of ecological forestry is something called natural disturbance emulation, or natural disturbance-based forest management. And basically what this is, it means simply that we use natural disturbances as a template or as a guide in terms of how we conduct our silviculture and forest management. And the success of natural disturbance-based forest management, it really depends on like two main things. The first one being is how well is the natural disturbance regimes in your area that you're working known. You know, you need good knowledge of that. And then the second thing is, well, to what degree then can natural disturbance regimes actually be emulated by silviculture and forest management? So in the case of Nova Scotia, our knowledge of natural disturbances was somewhat lacking, so which is a precursor, of course, to being able to implement ecological forestry. So the province there commissioned a broad study a couple of years ago on natural disturbance regimes and natural disturbance-based forest management. And it was quite a team of people from the province and some researchers from outside, including myself, to tackle this issue. And it was set up in two broad objectives. The first one being a review of the natural disturbance regimes in Nova Scotia. And then the second one being to develop a methodology for incorporating natural disturbances in forest management. So we started that work in 2019, I guess it was, and just finished it this past year. So the first part was reviewing natural disturbance regimes in Nova Scotia. And I'm not going to get too much into this today, but it was a big piece of work where we use a lot of empirical data, historical records and whatnot, to try to reconstruct what are the natural disturbance regimes of Nova Scotia. And through that work, what we uncovered was there's a lot of natural disturbances that affect the forest there, natural disturbance agents. But by far, the big three, the ones that disturb the most forest would be wind, primarily from hurricanes, fire, historically, and spruce budworm, the big three. They cause more than 80% of tree mortality. And just to put that into context, compared to a lot of these other disturbances, when we have one severe hurricane pass over the province of Nova Scotia, the way it sort of sits out in the Atlantic, a single storm can destroy more trees in one go than, say, 50 years worth of spruce beetle damage there. So wind being an important disturbance. And that work was summarized and published in a paper that we published 2 years ago. But the second part of the overall project was then, okay, we know something about the natural disturbances now, but how do you actually incorporate that information to help guide forest management? And so lucky for us, during the 1990s, Dr. Bob Seymour and Malcolm Hunter did a lot of work in this regard, and developed a framework for how to use natural disturbance regime data to inform forest management. And at the crux of this framework is basically the idea that most forestry decisions occur at the stand and landscape level. And at the stand level, like decisions related to natural disturbance-based forest management would be considerations that include, using silviculture to manipulate stand age, species, spatial distribution of trees, affect harvest rotation lengths, entry times, and methods of regeneration. And so I'd argue there's been a lot of work done in terms of ecological silviculture and how to design silvicultural interventions to emulate disturbances at the stand level. But I think there's less work to be done that's been done in terms of, at the landscape level. So, I mean, there's a lot of good work now, including, I sort of skipped over it there, but a good guide that just came out in the province of Nova Scotia about, basically a silvicultural toolbox of how to emulate natural disturbances at the stand level. But in terms of where to do that and how much to do on the landscape is where I think there's still some big questions to be answered. And so, and this is, of course, is the realm of forest management, which is used to govern the overall structure and function of the landscape. And some key considerations within forest management at the landscape level are, the spatial temporal distribution of stands, and then the regulation and scheduling of silviculture. So historically, most management situations rely on volume-based control methods for regulating silviculture, with emphasis on growth and yield, and less attention to the spatial structure of the landscape. But to do natural disturbance-based forest management correctly really requires more focus on area-based control of regulating and scheduling silviculture. And so just to emphasize what I mean by that, if we take a classic sustained yield example, so for instance, a forest landscape that's managed using even age silviculture, and let's just say on a 100-year rotation length. So if you manage that landscape like that with a rotation length of 100 years, where no stands permitted to age beyond 100 years or not cut before that, if you do that long enough on your landscape, you're going to get an age class distribution that looks something like what I have in this figure here, a rectangular distribution or even age distribution, where every year 1% of the landscape is harvested, which gets reset back to zero, and eventually you have a landscape of even distribution of ages between 0 and 100. Now that's a bit different than what might occur on a landscape where you only have a natural disturbance. And so a simple comparison would be if you take a landscape where severe wildfire is your predominant natural disturbance. In such a case, let's just say we have a wildfire with a 100-year return interval. In that case, rather than this rectangular distribution that we saw in the sustained yield example, what's theorized to take place is more of a negative exponential distribution of stand age classes across your landscape. And the main difference between the two and why that is that even though you have a 100-year fire return interval, that 100-year return interval, it refers to like the average time that it takes for an area in the landscape to receive fire again. But some areas can burn sooner and some areas can burn later. There's almost a pseudo randomness nature to it. And because of that, you'll have an abundance of young stands, but you have some areas escaping fire for a very long time. So then the question comes, well, how do you emulate that on the landscape? And so there's been work done in this regard. And one method of doing so would be, if you draw your attention to the red box at the top here, what we could do then is partition our landscape according to different rotation lengths that they're managed by. So in this case here, in this graph, what I've done, here's our negative exponential H-class distribution across the landscape from natural disturbance. But what we could do is maybe partition the landscape so that 30% of the landscape is managed under a 2% per year disturbance rate or 50-year rotation length. 50% of the landscape could be managed under 150-year rotation length, and 20% managed under a 300-year rotation length. And so by doing so, you're beginning somewhat to approximate that negative exponential distribution a bit more. And I just stuck in 3 partitions here, but you could put 4 or 5 or 6 partitions, however you want to do it. So that's great, perhaps for a landscape where fire is dominant, which is the case in a lot of areas of the Boreal forest where this has been played out. But for landscapes where you have multiple dominant disturbances, such as the Acadian forest region, where you have fire, wind, and spruce bloodworm taking place, so how do you implement it then? And so in doing some work on this, through our previous work, we're able to quantify the disturbance regimes for Nova Scotia in terms of mean annual disturbance rate, how much each year each one of them affects the forest there. And given the almost, again, pseudo random nature that these disturbances occur within certain landscapes in the province, it's not unreasonable then to expect that you can pool these disturbances together according to severity level if you know what the mean annual disturbance rates are. And so as an example, down here I have that multi-rotation model. So this would be a pooled multi-rotation model where in this case, the natural disturbance rate, high severity natural disturbance rate across our landscape pooled together, well, let's just say it's 1% per year, and it would create this approximate negative exponential curve. Well, you can again use that technique that we just talked about to try to approximate that. But the difference being here is that we're pooling together multiple disturbances. And so if you do this and do it according to severity level, because we know that each one of these natural disturbances, when they occur, they tend to occur at, well, high severity, moderate, and low severity levels. And if you pool these disturbances together according to disturbance severity, well, then you can begin to build pooled multi-rotation models, which you can apply to your landscape then to help guide area control management of your landscape. And then these different severity levels of disturbance could be emulated on the landscape using, well, high severity silviculture, intensive silviculture versus low severity silviculture or intensive silviculture, such as single tree management or something like that to that effect. So then the next thing is, okay, we have a method now of like representing these natural disturbances as a guide, but where do you apply it to? And so the key then is to, well, when we did our initial work, we characterize these natural disturbances according to landscapes in Nova Scotia. And fortunately for us, Nova Scotia has quite an advanced, mature ecological land classification system there. And so we use this in order to characterize the natural disturbance regimes to different landscapes within Nova Scotia. And so there was 10 of them in all that we ended up using. So for each one of these 10 landscapes, or forest types, I'll call them, we're able then to create these pooled multi-rotation models for each one of these landscapes. So in this example here in this slide, I have the pooled multi-rotation models for high severity disturbance. And I just want to draw your attention to the one with the red box here. So this one here is one we developed for 3 stand types or forest types: spruce pine and Acadian boreal wet conditions. And so in this case here, for these landscapes, high disturbance severity occurred at a rate of about 0.75% per year, or 133-year return interval. And so based on that information, then we could construct one of these pooled multi-rotation models, just as I described there, in order to try to approximate where the different rotation lengths should be represented on the landscape.
2 minutes.
Thanks, Mary. And so in this picture here, it's showing the spruce pine forest type across the province of Nova Scotia. So for that forest type, then, we can develop then pooled multi-rotation models for high, moderate, and low severity disturbance represented by different intensities of silviculture, and then use that as a tool, as a guide then in terms of, well, where we would apply these different rotation lengths or entry times for these various severities of disturbance or emulating through different intensities of silviculture. So that's where we got with that work, and that work was summarized in a recent paper we finished publishing last fall. And so that's where we are now. And so where we'd like to move from here with this is that we've developed these pooled multi-rotation models in theory, but before we go out and start cutting any trees necessarily, we'd like to test it out more to see, well, what are the effects on biodiversity and wood supply and other ecological, social, and economic values. So we started a new project where we're going to use a sophisticated landscape simulation model to test out these pooled multi-rotation models to see how it affects some of these values. And specifically some key issues we'd like to investigate would be things like, well, how does it actually affect levels of biodiversity, wood supply in the landscape when you employ these things? There's this interesting double dipping issue to contend with, which is the case where if we are emulating these natural disturbances and we're harvesting, doing silviculture at those rates, well, some of these disturbances, while some of them are suppressed, like fire and spruce budworm in Nova Scotia, some of them are still likely to occur, such as wind. So how do you contend with that? And so that's an important issue to investigate. And the last issue also of concern is climate change. You know, if we're going to base future forest management on historic natural disturbance regimes, well, how relative are they though in a future where the climate may change? So you could have changes in the natural disturbance regimes taking place, but also changes in the way the vegetation ecosystems respond to things. So that's something that needs to be taken into consideration. So that's all I've prepared today. So thank you for your time.
Thanks so much, Anthony. That was an excellent lead into the things that I want to talk about, and I hope will lead to a good discussion at the end of this session. So I titled my talk, "Do we actually want to emulate natural disturbances?" to be a little controversial, but also because this is what I think I really wanted to talk about. So as Anthony's explained, the natural disturbance-based management paradigm is based on the premise that we should be implementing forest management practices that either imitate or emulate the effects of natural disturbance, including type, severity, frequency, spatial pattern, etc. And at the landscape scale, this really pertains to what we create in terms of age distribution across the landscape, patch size, shape, connectivity, and this would be through mostly forest management planning. Implementation at the stand scale, the interventions would be in the realm of silviculture, controlling things like forest composition, structure, and a heavy focus on biological legacies, live and dead trees in particular, and multi-age structure of stands or size structure of stands. And the objective of all this, the idea we ever thought about this, was to achieve the objective of sustaining multiple values in our forest ecosystems: ecological, economic, and social. So when these ideas came out, which is now more than 25, almost 30 years ago or more, people started doing things and playing around with what this would look like. And we did this here in Alberta. So we established the EMENT experiment. This is the acronym for ecosystem management by emulating natural disturbance. Began this in 1997, put this very ambitious experiment on the ground with 4 mixed wood forest cover types, from deciduous dominated, 2 types of mixed, deciduous with the conifer understory, intimate mixture of deciduous and conifer dominated. And deciduous is largely trembling aspen and the conifer is largely white spruce. So on these 4 cover types, we applied retention harvesting treatments, which is one of the dominant harvesting approaches that has emerged around the world as a response to natural disturbance-based management. So we have 5 retention harvesting, from a clear cut to 10, 20, 50, and 75% retention, and then had a reference with 100% retention. Most of the retention was as dispersed green tree retention. You can see these pictures here, but we also had some patch retention. So each block had 2 patches, one small and one large, of aggregated retention. And so we applied these treatments, 6 treatments by 4 cover types by 3 replicates in 10-hectare compartments. Okay, we also have standing timber burn, and our idea at the beginning was to burn forest and use the burned forest as our reference for comparison to what natural disturbance would do, as wildfire being the dominant natural disturbance in the area we're working in the boreal forest of Alberta. We didn't get a lot of standing timber burns off. It turns out this is very difficult. It's either too wet, so the forest won't burn, or it's too dry, and the province is extremely nervous about allowing us to light a match. So we didn't get much in terms of standing timber burns. Later on, we did some 10% retention harvests with prescribed fire to try and address some of these issues of emulating wildfire. So I'm going to talk a little, very briefly, about some of the results that we've learned with continuous monitoring of this experiment since 1998, which was our main pre-harvest data collection year. And then I'm going to get into a discussion around the question, which started my talk. So let's look at what we found in terms of how the forest regenerates and develops. And so we have data from 15 years post-harvest. Here we have our 4 cover types, so conifer dominated mixed with the spruce under the aspen, and deciduous dominated, and in each going from the 2% retention, which is the clear cut with those 2 aggregated patches, up to our reference here on the right, so left to right, the gradient of retention. And this is basal area shown for spruce in blue and aspen in brown. So what do we see what happens with these harvesting treatments? Well, not surprisingly, basal area scales with retention. So higher levels of retention had higher basal area, except not really so much for deciduous. For deciduous, retention really didn't make that much difference in terms of basal area 15 years post-harvest. All stands had aspen natural regeneration, aspen suckering. So even the conifer dominated stands that had a relatively small proportion of aspen pre-harvest had a lot of aspen regeneration. Aspen does that. It suckers, even if there's 1 tree left, it'll be suckering. And this is also part of the natural succession of these stands. When they experience a severe disturbance, they go back to more aspen dominated and then transition over time more to conifer dominated. The conifer and mixed forests had more spruce component, particularly for the retention levels, the higher retention levels. Here we have 50 and 75 retention. So they had more spruce, and we're looking a bit more like the pre-harvest condition in terms of the composition. All the stands that had conifer prior to harvest got some good white spruce natural regen. We didn't plant any of these stands, so this represents what happened naturally. And so we ended up getting something that was more similar to the pre-harvest condition when we left higher levels of retention. Okay, the other main thing that we've been looking at is biodiversity, and I'm going to share some results. This is a work in progress. We're working now to do a big meta-analysis of post-harvest biodiversity recovery, including all the harvest levels at EMEND, and you can hear a little bit more about this in our special session tomorrow. So this is looking at the deciduous dominated forest. Here we're looking at recovery of species composition. So we're looking at percent similarity. So similarity in the species assemblage between the harvested forest and the reference forest. So reference forest, we've standardized this to 100% here. So this is reference forest versus other reference forests. And then this is the blue line is the harvested forest versus the reference forest. And we have over time, and for our different harvesting treatments here, from clear cut up to 75% retention. So this is for Staphyloid Beetles. These data come from Sung-Yil Lee. And you can see that in the early post-harvest period, there was a big difference between the reference forest and the harvested forest. And this slowly closed over time and was pretty well recovered by 16 years. And then we can see that by leaving retention on the landscape here, 10%, 20%, 50%, 75%, it closed this gap. so that the recovery was quicker, or even the change was minimal at even at the early post-harvest time periods. So this suggests that leaving retention can help with maintaining lifeboating, species biodiversity, and species composition for some groups. So this is in deciduous dominated forest Staphyloid Beetles. Here's vascular plant species composition, a little different story. In conifer-dominated stands, this is work with myself and Sam Bartels, who was a postdoc with me and now is at UNBC. We can see the recovery over time towards the unharvested or pre-harvest condition here, but really there's not a huge difference between these lines. So even with 75% retention, there was a fairly substantial difference between the harvested and the reference in the early post-harvest period, and the recovery slopes are pretty similar between them. So this suggests that actually retention didn't offer a lot of value in terms of maintaining the undestroyed plant communities or facilitating faster recovery. And then we have another example here for spiders. This is data from Jaime Pinzon et al., conifer-dominated forests. And this, this story shows that there was a very substantial difference in species assemblage between harvested forests and the unharvested reference forest. Almost no evidence of recovery over time, over a 16-year time period. There's no movement of these lines in this direction, and the retention didn't help with this at all. So basically we got a mixed bag in terms of what the value of retention was for achieving the objective, which would be to maintain or lifeboat, sustain biodiversity in these forest types. Okay, but the thing I really want to talk about is what should the reference be for these conditions? Here we're using the unharvested forest as our objective here. Sometimes we looked at it to say, the clear-cut forest was our reference, and we're saying, is some level of retention better than the clear-cut? So we can compare against these two ends. But often what I've got over the years from referees when we submit paper or from public discussions is that we should be comparing to fire. This is supposed to be natural disturbance-based management. Therefore, we should be saying what these harvesting treatments are relative to fire. And so I think I've struggled with that over time, and that informs the question of my talk. So I want to talk a little bit about some of the problems and challenges I see with the emulation of natural disturbance and where we're at with it. And some of these are described in this paper here, where we looked at, sort of did a critical assessment of how we could use fire regimes as the basis of forest ecosystem management. And this paper here, which is more recent with a bunch of collaborators from around the world, where we talked about retention forestry or retention harvesting and continuous cover forestry, two dominant practices that have emerged as the foundation of natural disturbance-based management, and whether they were actually enough for us to achieve our objective. So let's talk about what some of the problems are with natural disturbance-based management. We have lots of natural disturbances blow down here. Here's Hurricane Andrew effects in Florida, blow down in northern BC. We have biotic agents, insects, pathogens, beavers. We have wildfire, dominant disturbance in much of the boreal forests in Canada. These disturbances are highly variable in terms of temporal and spatial aspects, in terms of their frequency, severity, spatial extent, pattern. They interact with one another, they're cumulative, and this makes it very challenging to try and understand them and to emulate them. The main point is that none of them look like this. None of us can realistically say that there's any natural disturbance that takes the boles of trees and moves them off down the highway. We're never going to be able to do this and say that it's really like natural disturbance. Okay, so in some of the details and some of the other problems, the high interannual variability, and thanks Anthony for the good description of how we would take disturbance frequency and turn it into an age class distribution. The challenge is that, that lovely negative exponential age class curve is based on the presumption that the same amount of forest burns every single year. We know that's not true. Here's area burned, a somewhat old database, but we know that the area burned is highly variable year to year. And so if we actually incorporated this variability and looked at what it would result in terms of an age class distribution, we get, a dog's breakfast. So my colleague Glenn Armstrong looked at this, more than 30 years ago, a long time ago, and did some simulations and said, what would be the outcome for landscape scale distribution if you actually incorporated this interannual variability? And the answer was that basically you could get almost anything, any age class distribution, and say that it was the result of natural disturbance regime.
1 minute.
Okay, I'm going to skip over this, sorry. Most fires are small, but large fires dominate the landscape. We have internal heterogeneity in fires, and so a lot of areas experience low severity disturbance, and only some areas experience high severity disturbance. We have unpredictable outcomes, so sometimes forests change composition from pre to post disturbance, and so would we actually want to emulate that? And so there's a long list of problems with the emulation of natural disturbance. We don't have them characterized well. They don't affect the landscape in a random way. They sometimes are more severe than harvesting. They change over time. And so what should we emulate? And so the question that I wanted to pose is, do we actually want to do forest management that makes the landscape look like this? Or do we want to do forest management that brings us back to this as quickly as possible? And how are we going to do this? How are we going to learn from nature to implement forest management practices that will help us achieve our objective, which in the first place was just to sustain the structure, function, biodiversity, and the diversity of values from our forest landscapes? And I hope that we'll get a chance to discuss that in our time at the end. So thanks.
So hi everyone, I'm Nelson. I'm a research scientist with the Canadian Forest Service. I'm talking to you from my home in Quebec City in Eastern Canada. Obviously, English is not my first language, so I apologize in advance. I will be reading my notes, so I won't be looking too much for my words. I want to thank Stephen for his invitation to be part of this session. I'm both honored and humbled to be part of such a list of speakers. And also, I want to acknowledge my co-authors. We're also all part of the Canadian Forest Service. Instead of a list, in fact, I should probably have put their names on a map. So this way you would have seen that altogether we covered the country pretty much from its most western point to its eastern limit. So today I want to talk to you about an ongoing project that we believe is of interest to the theme of natural disturbance emulation, namely gathering the available knowledge about post-disturbance recovery phase of stand development. So as a general context, and similar figures have been presented earlier during the conference, Canadian forests are submitted to major large-scale stand replacing disturbances. And here are the numbers available from the last report on the state of Canada's forests, where we see that insect outbreaks, harvesting, and wildfires are the main disturbances shaping forest landscape across the country. Now, we think that the post-disturbance recovery phase is of major importance when trying to understand natural and anthropogenic disturbance effects on stand dynamics. So for example, looking at this simplified diagram, we can see that from a forest regeneration perspective, there are multiple critical pinch points where regeneration success can be jeopardized. So Dr. Balzer, in fact, addressed this in a much more complete and comprehensive manner in her keynote speech earlier this week. But in a nutshell, if we start with a mature forest stand submitted to harvesting, a proportion of the advanced regeneration will be eliminated by the operations itself. Then seeds available in trees either before or after harvest will be submitted to predation, to parasites, or so that's some of them won't even make it to the seed bank. And once in the seed bank, a proportion, usually a large one of the seeds, won't receive the stimuli necessary to go from a dormant to an active state and will simply die and decay, while others will be submitted to predation as well. And from the seedlings that will germinate, a proportion won't be recruited at all in the regeneration layer, as they will die from various biotic and abiotic factors, such as browsing, competition, or water stress. So all in all, this is an illustration of why the post-disturbance recovery stage is such an important impact on stand development for years to come. Having said that, I now want to point that as the Department of Natural Resources Canada, the Canadian Forest Service has, as part of its core mandate, the role of providing scientific knowledge to support sustainable forest management in Canada, which largely relies on ecosystem-based management inspired by natural disturbances, as pointed out by previous speakers. And as you can see here, the CFS research programs are largely organized around the main disturbances shaping Canadian forests. So, given the importance of the post-disturbance recovery phase of stand development and the mandate of the Canadian Forest Service, we had to review post-disturbance research in the organization and thus have a comprehensive overall view of available knowledge. For us, this was a step that we felt was necessary to ensure that this publicly funded research is accessible, well integrated, and could foster collaboration both internally and externally. So a first step for us to achieve this objective was to formalize our ideas about this post-disturbance recovery phase. We did this by drafting a framework representing the various factors affecting stand recovery after natural and anthropogenic disturbances, and identifying some of the key variables that can help assess the state and mechanisms of recovery. I don't pretend that this is a comprehensive framework, meaning that some boxes or variables are most probably missing. But this was anyway for us useful to organize our thoughts and organize our following work. So in summary, when going from right to left, we've identified the large-scale factors such as climate and climate change as being important drivers of disturbance regimes, recognizing that synergies or interactions exist between disturbances and that climate change also affect forests at the stand level. And then at the stand level, we distinguish stand replacing disturbances from partial disturbances, and further recognize that some stands will experience regeneration failures while others will go through normal forest recovery. And this is also a theme that was addressed by Dr. Balzer earlier this week. Finally, we've listed key variables enabling to evaluate or monitor recovery, and we group them in broad categories, namely soil, hydrology, vegetation, and wildlife. So once we had our idea organized regarding the post-disturbance stage, we conducted a literature review. We focused on studies pertaining to one or more of the disturbances shaping Canadian forests and addressing response variables we had identified in our framework. It's important to note here that given our objective, we restricted our search to research papers for which at least one author was affiliated with the Canadian Forest Service. This means that the list of studies absolutely don't cover the whole post-disturbance research in Canada. However, given that CFS researchers are dispersed throughout the country, are in most cases collaborators with academic partners, and that CFS programs explicitly address themes related to post-disturbance recovery, we believe that this sample of studies is representative of Canadian research on the topic. Also, important to note is that our search was limited to empirical research studies published between 1998 and 2020, involving on-site inventories or measurements. So modeling studies based on data collected elsewhere or from national or provincial inventory database were not included here. So as a result of this search, up to now, we've identified 181 publications. On this map, we have plotted the location of the research sites where the research data was collected in these studies. So one study can be represented here by more than one site. This map allows to see both the wide distribution of research sites across the country and also the diversity of disturbances or combinations of disturbances that have been studied. You can also see that the majority of the study sites are located in the Boreal zone of the country. Going through each study, we then extracted metadata describing not only the type of disturbance, but also the variables that were assessed. So to represent research topics and focus, we summarized the data using alluvial diagrams. So to build these, and given that our focus was really and is still on available data, we use what we call evidence points, being a discrete measurement event for a given study after a given disturbance type and or severity type. So evidence points can also represent temporal redundancy when a given study site was, for example, remeasured multiple times for the same variables. In these alluvial diagrams, the vertical position represents of an item represents its importance relative to the others, the most important ones being at the bottom. So the first thing that we observed was that forest management, namely harvesting, was the most studied disturbance in the literature we reviewed, followed by fire. Despite the fact that large forested areas are affected annually by pests, studies on recovery after pest outbreaks were scarce. Other disturbances such as mining and seismic lines or other abiotic disturbances were marginally found in the CFS literature we reviewed. We then created graphs for each disturbance type to see what variables and processes have been documented in these studies. Here's an example for the forest management category. So as you can see, most of the variables studied after forest management disturbance related to vegetation, mainly tree regeneration, including plant physiology and nutrition. Data on understory species diversity was also quite commonly reported. Soil chemical characteristics was the main soil variable studied after forest management. Wildlife diversity was the main topic for studies, including data on animals. Studies including hydrological variables were quite marginal. As a second example, here's the alluvial diagram of evidence points for studies conducted following wildfires. As for the forest management category, vegetation-related variables were highly dominant, with tree regeneration being the most frequent variable measured, followed by understory diversity, deadwood, and data related to wildlife diversity. So the climate is changing, and changes will be even more important in the Boreal biome, an ecozone that spans across Canada and of major importance for the procurement of fiber and other ecosystem services such as carbon sequestration. The post-disturbance recovery stage of stand development will become even more critical in shaping future forest landscapes, as tree regeneration is highly sensitive to the stressors brought by climate change, as we've shown in a recent review paper published 2 years ago. So in this small study, we are showing that the Canadian Forest Service has a national portfolio of published research and ongoing projects about post-disturbance recovery, a theme that we think is central to natural disturbance emulation. Our efforts are now focused on integrating this information into a comprehensive database to identify research priorities, enable meta-analysis, and foster collaborations. Our preliminary analysis that will eventually be completed with studies from outside CFS suggests that some disturbances are understudied relative to their annual imprint on Canada's forests. And here we can certainly think about wind and insects. So thank you very much. I hope it was useful. Thanks.
So I am going to give you something completely different. We're moving south of the border into the US in Minnesota, and also downscale to really the stand scale perspective of this. And really our work in my group is very much focused on an understanding how forests develop over time in structure and composition, and then how we translate that into silviculture. So that's my perspective. Give you a little bit on concept and context, and we're going to use this windstorm disturbance case study that's been around with us a long time. And the whole idea is how do we look at a study or a disturbance like that and think about how to get closer to emulation with silviculture. And I would just say that this is a forest type that has been largely off limits from an end perspective in our part of the world, in the lake states in the US, because of the timber value. So just a little bit on concept. So I would point out this. Me, Tony D'Amato, Jerry Franklin, Norm Johnson, and I have been talking about ecological silviculture for a while now. And we conceptualize it as a toolbox to manage forests as whole ecosystems based on emulation of natural models, and then explicitly incorporate some ecological principles. So it's really more than just emulation of disturbance in our take on this, but that's an important part of it. And so that's what I'll focus on here. One of the goals for this approach is really to reduce the disparity between a healthy natural ecosystem and a managed counterpart in terms of structure, composition, and function. And we need to think about how close we can get based on understanding natural disturbance. So these principles that I mentioned, we talk about 4 of them: continuity, complexity, diversity, timing, and context. And it's really continuity that I think has the most relevance to thinking about application of end or interpretation of natural disturbance and using it in management. So that'll be my focus. We talk about this as continuity in forest structure, function, and biota between a pre and a post-disturbance ecosystem after a regeneration scale event. So we're not talking about little, small scale disturbances. And as others have said, that's the whole idea behind biological legacies. And functionally, it's what leads to ecological memory and that idea. And really it's implemented, as Ellen talked about, as part of a regeneration system that involves retention in managed forests. So that's kind of the concepts I want you to keep in mind. So let's look at continuity in what I'm calling aspen mixedwoods when managing for timber. Is there any? Well, generally, this is, and that's just kind of generalized here, but this is the silvicultural system that a lot of people use in an aspen-dominated forest. There isn't much to it, right? And so where does continuity come into play? Well, for us in Minnesota, we do have voluntary forest management guidelines that talk about retention. So over the last 20 years or so, we've gone from a photo that looks like that to applications like this that have some low level of retention, oftentimes in patches like that, small patches, or a low number of small trees. Well, how close is that to a natural model of continuity for an aspen ecosystem? Well, it's not very, as you can imagine, but what could it look like? So what I want to do is talk about this case study, disturbance study of a large windstorm in an aspen birch basswood mixed-wood system. That nomenclature is from the state of Minnesota's ecosystem classification guide. And this particular ecosystem has both wind and fire disturbance and maybe a rotation of about 130 years. It's mixed wood, and then it should have 9 overstory tree species, but aspen oftentimes maintains some dominance over time, as long as there's disturbance. And you can see where it's at. When Stephen asked me to do this, I questioned whether we work in the boreal forest. We kind of don't, but this forest type is probably similar to some that occur within the boreal zone. And the study that we worked on is really right there in that part of Minnesota. So let's look at this windstorm case study. The objective was really to quantify structure and composition after the disturbance. And my goal was to demonstrate what typical aspen management is missing and what it could include if we start quantifying post-disturbance structure and composition. We do this in different forest types, but in this case in aspen. And so this was on the Chippewa National Forest, which you can see north central Minnesota, this large area. Calling it a mixed wood, but it was definitely dominated by trembling aspen, about 70 years old. And this was actually one of the first things I ever worked on when I came to the Forest Service, the U.S. Forest Service, but we've been following it over time. And the neat thing about this is there were a large number of very discrete blowdown patches that we were able to quantify with hard borders and no disturbance in between. So we did that. We took a bunch of them, we measured structure, composition, and eventually I'll get back to, this morphed into a salvage logging impact study with and without prescribed fire. But there's the size distribution of patches. So they range, from small to maybe 18 hectares in size, but most of them 4 hectares or smaller. So one of the things I wondered about is, how's that compared to the average clear cut size in Minnesota? And this was a report in 2017 that said, average size was around 7 hectares. So an interpretation of that is our patch size is not too far off our clear cut patch size relative to this disturbance event. But it's really what's going on in the patch that's most important in terms of continuity. So we looked at residual tree density, and this is by patch. So the x-axis are patches we measured, and you can see that it's highly variable internally spatially. So a lot of heterogeneity in residual trees, but generally a lot. So this was a big regional windstorm as well, but it had a lot of structure left. So maybe 150 trees per hectare, something like that. Here's what Minnesota voluntary management guidelines say about leaf trees in clear cuts for upland mixed forests, which this is like 24 to 30 trees per hectare, 15 centimeters or greater. And also there's a recommendation about clumps of 10th hectare or greater on 5% of the area. But they talk about locating those around seasonal ponds or other resources that you might want to protect. So my interpretation of this wind event to the guidelines is that density recommendation is very low compared to the natural model. And clump location is not going to be specific to a feature like that. Another thing we looked at is residual tree size distribution. This diameter just pulls all the trees in the patches, and you can see how that falls out, which, the larger trees are 30 centimeters and above, and mostly aspen because it was dominated by that. Here's what the guidelines say. 50% of the few leaf trees you leave should be 30 centimeters or greater. So my interpretation is the size recommendation for leaf trees is reasonable on paper, but there's this laundry list of exceptions that you can invoke to not leave large trees or very many of them. So the end result is something like that photo you see there with very few small diameter, often unmerchantable trees getting left in the name of this guideline. The last thing I'll show with this is we looked at dead trees, and this pulls both snags and trees on the ground, so it's everything. And not surprisingly, there's a lot of dead trees. It's highly variable among the patches, but still quite a few. Here's what the guidelines say about this. Retain all snags possible and create a greater than 15 centimeters. And create or retain at least 5 to 12 pieces of larger dead wood per hectare. Well, there's the size distribution of aspen, of dead aspen, and you can see that it's 30 to 35 centimeters on average. So the interpretation is that most snags are going to be, after natural disturbance, much greater than 15 centimeters, and there's going to be way more than 5 to 12 pieces of dead wood per hectare, not surprisingly. So let's come back to this question that I started with. Natural disturbance, how close is close enough? Well, you know, you only, and Ellen referred to this, you only can get so close when managing for timber. We all get that and understand it. But our numbers for this case study suggest that typical aspen management is a long ways away. Okay, has a long ways to come, but it doesn't. And why is that? Well, it's this. There's this concern that retention of even low levels of overstory greatly reduce aspen suckering and growth. And the numbers people talk about from a publication in the 70s, that 2 to 3 square meters per hectare reduces growth, you know, a third or more of aspen suckers. And so it's probably a legitimate concern. And we have looked at that in different studies. So here's an example of that. This is sucker development after 3 years. On the left, that just shows height and biomass in a clear cut versus leaving 12 square meters per hectare basal area. And then there's the development of sucker density over 3 years. And people in our part of the world talk about 11,000 stems suckers per hectare as being a minimum stocking layer. So you can see that with retention, you're getting below that by 3 years. And it probably only gets worse over time. So here's back to the Windstorm study 12 years later. And again, we measured after blowdown, and then some of the patches ultimately were salvage logged soon after the blowdown, and others had prescribed fire after the salvage logging. And that's what this is showing here. These are sapling-sized suckers of trembling aspen. And there's confounding of the influences here, obviously. But on the left, that's unsalvaged. There was about 7.5 square meters per hectare of basal area, overstory left, and all the dead wood. The salvage reduced that overstory a little bit more, and no dead wood, and then the burning even more. So we're not teasing out the differences in those influences. But the point here is that if you look at sucker development after that disturbance and use that as your guide, that probably is going to matter in terms of aspen production, enough that people care. But then I go back to where we started. Recall this ecosystem. And this is the most desirable ecosystem for managing for aspen in Minnesota, this somewhat more mesic mixed-wood system where aspen does the best. So it's valuable from that standpoint. There's supposed to be 9 overstory tree species in some abundance in that ecosystem. And if you're interested in that, more of the ecosystem management approach, then you probably want less like those 2 pictures in the middle and more like a true mixed-wood system where you're having patches of aspen along with other species. So what I'll just end up here with summarizing a few points. And again, going back to this is ecological common sense that oftentimes doesn't find its way into silviculture in our part of the world. So we know that this complex structure that results from a disturbance like that is very different than what happens with timber management for aspen. No kidding, right? It's obvious. But the point is that residual tree, snag, deadwood guidelines that we have are better than nothing. I started like looking at these kinds of things 25 years ago, and we had nothing then. We have something now, but they're not very close in terms of the outcomes at the stand scale of natural disturbance. The concern about aspen productivity, it's valid if your goal is to maximize fiber production from aspen, which it is for a lot of ownerships in our part of the world. But it's not so valid if we take this broader approach of managing for a range of ecosystem services in mixed species forest. And I will finish up with that. Thank you.
Hi, everyone, and thanks to Stephen for inviting me to join this session. And thanks to all the great talks that came before me and have highlighted some things that I wanted to touch on today. Now I will flag, and I flagged this with Stephen when he asked me to join this session. I don't directly work on natural disturbance management, but he wanted me to talk a little bit about some of the changes we're seeing in response to wildfire in Canada's Boreal that may impact, impacts of our decision making about natural disturbance emulation. So that's where I'm going to go today. Oops, there we go. Yay, it worked. Okay, so natural forest management, we've had all kinds of great information about what that looks like and how that is, the goals of natural disturbance emulation. And just to kind of recap on that, what this is trying to accomplish is using natural disturbances. So the size and the frequency of these natural disturbances, the severity of these natural disturbances to guide silviculture and restoration management goals to take systems back to what they were pre-disturbance. And so in the Boreal, the most common, so here's our most common stand replacing disturbance, natural stand replacing disturbance, which is wildfire, large stand replacing wildfires. And the most common natural disturbance emulation method in the Boreal is clear-cut harvesting. And so the idea, with both of these, you have large areas that are disturbed, an even age stand that comes up. There's lots of differences between these as others who have spoken in this session have identified, and that's not really my goal here to get into those differences, but what I wanted to touch on is this aspect of the natural range of variability, which is really important in dictating, what that emulation looks like. And, how you're going to manage these landscapes to try to, emulate these kinds of natural disturbances and achieve those management goals. Okay, so when we think about natural range of variability, we think about these long-term normals where we've got, variation around a mean, and Ellen showed some really nice variation around in terms of area burned, I believe it was. But that, you're kind of moving around some longer term mean. Now, the challenge that we face right now is that we're in a period of really rapid climate warming, and that's happening really, some of the fastest warming we're seeing is in boreal ecosystems. And what this climate warming means for natural disturbances in boreal systems is a loss of stationarity in the boreal fire regime. And so these are data from Western North America showing the burned area as a function of time. And we see this increase in burned area through time. We're also seeing changes in fire size. We're seeing changes in fire return interval, in severity of burning. So we're having, pretty remarkable changes in the fire activity on the landscape. And this is projected to continue, not surprisingly. We have a climate that's warming, more fuel on the landscape as a consequence. And, in many parts of the Boreal, increases in lightning activity as well. So you have more fuel, you have more ignitions, and this leads to a change in fire activity. And so these plots are showing for 2020, 2050, and 2080, changes in annual area burned, annual number of fires, and mean fire size. And these are modeled values from this Wang et al. Paper in Science of the Total Environment. And what you're looking at is the darker the color over here, the larger the fold increase. And so these vary from 5 to 10-fold increases in these metrics from current day. And so not only have we seen historic changes in what the area burned and some of these other metrics of fire activity, but we're also seeing projections that suggest fire activity will become much more intense on the landscape. And so this leads to some pretty big challenges when we think about this loss of stationarity in fire activity. And so the first of these is, I think Ellen did a really nice job highlighting this, but what is it that we're trying to emulate? Moving forward as this, as our kind of target changes with climate warming, what is the goal of what we're trying to do with natural disturbance emulation? And the second, and this is what I'm going to spend a little bit more time on, is, how might these rapid warming induced changes in fire activity affect landscape level decisions about forest management? And both Anthony and Ellen spoke to this, and Anthony, I think, referred to it as double dipping, I guess. We have, a forest landscape, and the disturbances, the natural disturbances, are becoming more frequent in the landscape, more severe in the landscape, and it's altering. We have other values that we want to consider. And so I'm going to touch on a couple of those and how changing wildfire regimes impacts those, to put this in the context of, what we need to be, maybe some of the other values we need to be thinking about in the context of landscape level management. And so these are both really nationally important considerations. So woodland caribou are a species at risk in Canada and in many of the provinces. This is a species that requires, mature forests to be successful, and a pretty large intact area of mature forests. And so the management plan that has been developed for this species suggests we need 65% of the landscape to be in an undisturbed state, and this includes both fire and other disturbance agents. And the second piece is net zero emissions by 2050. So this is the banner taken from the Government of Canada website, and we see this nice active transport and green energy, and then we see forests. And Canada is a very forested country, and we are placing a lot of emphasis on the role of forests in as natural climate solutions to get us to this net zero emissions point by 2050. Okay, so to jump into the first example of this landscape level consideration, when we think about kind of intensification of wildfire on the landscape, this is what it looks like in the context of Boreal caribou ranges. So this is for Western Canada, and we can see each of these sort of blobby shapes is the different Boreal caribou population, and overlaying on that is fire perimeters. And so the darker the reddish color, the more recent, and you can see lots of dark reds and oranges. And some of these populations, you can see this one down in Alberta that crosses the Alberta and Saskatchewan border. Almost the entire range of this particular population has been disturbed by fire in the last 20 years or so. So, these are the changes in fire activity we're seeing in the landscape has really big implications, direct implications for some of the requirements we have for this particular management issue. So there are these direct impacts of disturbance that lead to an increase in proportion of the landscape that's in a disturbed state. And we see for Boreal caribou, there's strong negative selection against these burned areas, particularly in wintertime. So this points toward the need to think about how are we maintaining these undisturbed portions of the landscape to help to support this species and others in these multi-use landscapes. A second piece of this is that there's indirect impacts, and so these are data that I showed on Tuesday, but we're seeing this loss of resilience of a really important part of the landscape for a species like caribou. So black spruce lichen forests are forests that caribou rely on quite heavily, and we're seeing with the fire regime that we currently have a shift away from black spruce and toward other taxa. So these red and yellow and orange bars are places where black spruce has lost resilience in the landscape. So we have other species recruiting at higher levels or total failure for black spruce to regenerate in many cases. And what this looks like when we take a look at these sites, and this can be up to 60% in some of Western Canada. When we look at what this translates into, we see lots of parts of the landscape where forests are failing to regenerate. So it looks something like this, but lots of other parts of the landscape where we have deciduous taxa coming in and replacing black spruce. And so we have forests that look more akin to this. And these are not great habitats for a species like caribou. So we kind of have this double whammy of more disturbance on the landscape and landscapes regenerating in a way that doesn't support the needs of this particular species. So this is an example of these direct and indirect impacts on biodiversity at the landscape scale. The second piece has to do with emissions, and I'm just going to highlight some work we did on carbon emissions from a big fire year in the Northwest Territories. So in 2014, about 3 million hectares of forested land burned in the Northwest Territories. In addition to looking at regeneration, we quantified carbon stocks in sites across quite a number of these fire scars, and we're able to use landscape level predictors to scale this up to all of the fire scars that occurred in that particular fire season. And so you can see that the darker the color, the greater the carbon emissions from that particular portion of the fire. And so what we found is that these large fire years emit a really tremendous amount of carbon. So in total, this equated to about 94 million metric tons of carbon dioxide that was released by fire. And this equates to half of all the carbon dioxide that's absorbed in a given year by Canadian ecosystems. And so when we're thinking about meeting these goals of, zero net emissions by 2050, we need to be considering this changing fire regime. And what does that mean in terms of emissions? And what does that mean in terms of what we can do from a management perspective? And then just to follow up on that, this relates to legacy carbon. And so in addition to having a very large amount of carbon emitted from these forests during this particular fire season, we also found that legacy carbon was released during this severe fire event. And so when we think about the importance of boreal systems as carbon storage, as a carbon storage unit on the landscape, the way this works is mostly through the soil. It's not really through the trees. And we have, carbon that accumulates in fire-free intervals. Some of that's burned away in the next fire, but some of it remains. And so then you build up more peat on top of that previous, that previous carbon that was laid down. And so this grows, and you have these lovely carbon stocks stored in the soils in these areas. What we found is that in landscape positions that were drier, we saw an increased probability. So legacy carbon is that carbon that's older than the stand age. So carbon that was sequestered in some previous fire-free interval. And so what we found is that there was lots of legacy carbon on the landscape, and that we were most likely to lose that legacy carbon during fires when we had drier sites, or when we had sites that were younger, so a shorter fire return interval. And so this is what this is depicting, where you have short fire return intervals, that carbon that was accumulated in the previous fire-free interval is consumed, and you gobble into the previous fire-free interval's carbon, or even deeper. And so we're releasing carbon to the atmosphere that hasn't been interacting with the atmosphere for quite a long time. Okay, so I guess where I wanted to end here, and I hope I haven't been too fast. I haven't seen Marie-Josée pop in again. But where I wanted to end here is that we have all of these additional pressures of this changing stationarity, or the loss of stationarity of the fire regime that's driving changes in how much of the landscape is disturbed, changing how that landscape functions for important things like carbon storage. And can we justify continued emulation of wildfire through clear-cut harvesting in an increasingly fiery boreal? And the other component of this is an increasingly disturbed boreal. So this is, I included this because we were talking about this on Tuesday, but here we have willow miner. So we're, seeing increases in herbivory and pest outbreaks in boreal ecosystems. This also really alters how those systems function from a carbon and a carbon perspective in particular, but can lead to various aspects of land cover change. And direct impacts of climate warming through drought-induced mortality, like we see in Aspen in this image. So we've got all of these changes that are happening in tandem with climate warming, and so thinking about how does emulation of natural disturbances fit into this with a, a moving target and changes in the way the landscape can support additional disturbances. And with that, I will thank you, and hopefully I haven't gone over time, Marie-Josée.